I'm going to talk about classification of systems. So the systems can be classified as follows. The first classification is static system and dynamic system. The static system is also called a memoryless system. Okay, and this dynamic system is also called a memory system. And the second classification is linear system, linear and non-linear system. And the third classification is time varying system or time invariant and time varying system. And the fourth classification is causal system and non-causal system. And the fifth classification is stable system and unstable system. And the sixth one is invertibility and inverse system. When I say inverse, of course, obviously I can have non-inverse system. So these are the main classifications of systems. Of course, you can have one more classification, something called continuous time systems and discrete time systems, but it will not come under the properties of systems. Okay, so these are typically, these first six are typically properties of systems. So based on that you can classify the system. So let us first talk about static system versus dynamic system. Okay, so the definition goes as follows. A static system is one in which the output depends upon the input at that time and nothing else. So the meaning of the statement is as follows. It does not depend upon what happened in the past history, or the past history of the system is immaterial. Okay, suppose you give x of t and it gives rise to y of t. Now at present, let us say at time t equal to, now time is 4:43 p.m. Now if you want to know the output at 4:43 p.m., then the output exactly depends upon at time t is equal to 4:43 p.m. Okay, at least bother about what happened at 4:42 p.m. or 4:41 p.m. and so on and so forth. Therefore, the present output exactly depends upon the present input. Such systems are called static systems. The static system is also called a memoryless system. That means it will not remember what happened in the past. That's what we mean by memoryless system. That means here this t is an independent variable, as I said. T is the independent variable. So the output for each value of the independent variable at a given time is dependent on the input at only that same time. As I said, if I say 443, at same 443. So this t is the independent variable. The best example for static system is a network which consists only resistor. Okay, so therefore an electrical resistor is an example for memoryless device, and the circuit which is made up of the resistor, then you can call memoryless system. Okay, so the current in the resistor depends only on the voltage at that particular point of time, because we know the relation between voltage and current in the resistor. You have a potential source, let us say V, then put a resistor like this, like that. Then this current I depends at, let me take simple example, I do not want to take a big one. Okay, so let us say R1 and R2, where I is equal to V by R1 plus R2. There is no time parameter here. The moment you make V to 0, then suddenly the I also goes to 0. Okay, so the current in the resistor depends only on the voltage at that particular point of time, not that how that voltage has come about in the past, not about its rate of change of voltage, etc. Okay, it depends just on the voltage at a particular time dictates the current in the resistor. So if a resistive network is there as one port resistive network, its input voltage is given, the current is immediately deduced by the magnitude of the voltage at the particular point of time. So static networks are also sometimes called, as I said, memoryless network or memoryless systems. Or memoryless networks. So static system. Okay, now let us talk about dynamic systems. Okay, so on the other hand, in dynamic network, it is not enough if you know the instantaneous values of the input at that time. So whatever the thing you know at present, that is not enough to determine the output. We should know something more about the input, like what happened in the past. So we should know perhaps a kind of summary of what happened in the past. Suppose let us take an RLC network. If you want to know the response of RLC network, okay, so to an impressed excitation, this is my excitation. You should also know what is the initial charge in the capacitor, what the initial current in the inductor is. Okay, so in order to find the response of the RLC circuit, in addition to the excitation, this one, you also know what the initial charge in the capacitor is and what the initial current in the inductor is. Otherwise, you cannot determine the or find out the response of the RLC circuit. So in a dynamic system, the response depends not only on the instantaneous values of the input, but also on the derivatives of the input and also the integrals of the input. If you take a resistor, then it is a simple algebraic equation. When I say algebraic equation, no integration and no differentiation. okay, for static networks or memoryless networks. On the other hand, if you consider dynamic system or memory system, then the final equation contains derivative of the input, integral of the input, and so on and so forth. So it does not merely depend upon the instantaneous values. It also depends upon the rate of change of input, how fast the input is changing. The integrals or integral values of the input, the past history of the input as summarized by the initial conditions. So initially how much charge is there in the capacitor. Before you switch on, let me put a switch here, and before you close the switch, how much charge was there in the capacitor. So these are the things that I need to know before I want to find out the response of the circuit. So the best example is an RLC network. So if you are having an RLC network with a given excitation functions V, it is not enough to know the complete solution. In order to find the complete solution, you should also know the initial current through the inductor, how much current was flowing in the inductor before you close the switch, and what is the initial charge which is present in the capacitor. These two are we need to know. So these are called the initial conditions, that means past history. Therefore the present output depends past history. What is the past history? The past history is before you start to work on the circuit, the inductor may have some amount of current I suffix 0 and the capacitor may have some charge C suffix 0. So it turns out that when you want to describe a static system, the equations governing the performance turns out to be purely algebraic in character. Whereas in a dynamic system, we need to take stock of the derivatives, the time variation of the various quantities. So we finally end up with differential equations. Okay, of course, an differential equation is nothing but the equation consists of integration plus derivatives plus some algebraic terms. So whenever you have no equation like this, then this equation can always be reduced to a differential equation. It's not a big deal. Therefore, in general, we can say that it contains differential equations, or you can say integral differential equation. So let us note down the important points between static and dynamic systems. Static or memoryless, and here dynamic or memory systems. Okay, so here you have resistive network or system which contains only resistors, and here the example is Rlc, it contains both inductors and capacitors. Here you have purely algebraic equations, and here you will have integral differential equation. The integral differential equation can be reduced to differential equation. It is not a big deal. Okay, so that's it about static and dynamic systems. And next, let us talk about linear systems. So in a linear system, I am talking about continuous time system here. Okay, now our discussion will be mostly in terms of continuous time systems. Once if I finish about continuous time system, then I will talk about discrete time systems. Okay, like in the later point of time, we will talk about discrete time systems. Now in a linear system, let's say you take a system and the input is x1 of t. Let me call the input is x1 of t and the corresponding output is y1 of t. So x1 of t gives rise to y1 of t. Now what you do, take the same system, don't change the system. Now instead of x1 of t you give some other input, x2 of t. Now your system produces y2 of t because your input is different. So x2 of t gives rise to y2 of t. Then for a linear system, no matter what x1 of t and x2 of t are, a constant times, let's say a times x1 of t plus b times x2 of t will give rise to a times of its corresponding input y1 of t plus b times y2 of t. Now again you are not changing the system, the same system here using, but now what you are doing is you are taking x1 of t multiplying by some constant a. That constant is some amplification factor. Let's say you are amplifying 5 times, so where a is constant and b also constant. Okay, so if any system will give this kind of relation, then that system is called a linear system. Okay, so this equation holds for all values of a and b, where a and b are constants. Okay, so x1 of t gives rise to y1 of t and x2 of t gives rise to y2 of t. Then you take a linear combination, c1 times x1 of t, a times x1 of t plus b times x2 of t, which gives rise to a times y1 of t plus b times y2 of t. This is the linearity property, and this is what is referred to as the principle of superposition. Okay, this is called a principle of superposition. Now sometimes people break this superposition into two parts. The first one is homogeneity and the second part is additivity. In fact, if you break the superposition into homogeneity and additivity, then it is very easy to check the linearity of the system. So what we are saying is, if x1 of t gives rise to y1 of t, then a times x1 of t gives rise to a times y1 of t, and this is called a principle of homogeneity. Okay, so then the second part is like as I said, x1 of t gives rise to y1 of t and x2 of t gives rise to y2 of t. Then x1 plus x2 of t gives rise to y1 plus y2 of t, and this is called additivity. x2 of t gives rise to y2 of t, then you add these two guys, x1 of t plus x2 of t, again give to the same system, which gives rise to y1 of t plus y2 of t, and this is called a principle of additivity, because you are adding the two signals, so it is called additivity property. So if you combine this principle of homogeneity and the principle of additivity, then you will get a superposition. Okay, so this is the class of systems which are called linear systems, one which obeys the principle of superposition. And most of the electrical networks that we have solved earlier, that we have considered, or that you will study in circuits and networks, belongs to this class, linear systems. But you must keep in mind that the superposition principle will be valid, for example, in the case of electrical circuit with zero initial conditions. This is a very important point. Please remember this. Superposition is valid only if initial conditions, only in zero initial conditions. Zero initial conditions. What do we mean by zero initial condition? When I say zero initial condition, initially the charge in the capacitor is 0. Initial charge equal to 0. Current in the inductor is 0. This is what we mean by zero initial conditions. If capacitor has got some stored energy in that, then the principle of superposition will not be valid. Suppose you take a capacitor in the circuit and that capacitor has some initially stored energy, then the superposition will not be valid. Okay, now it's time to take some example to see the linearity property. Therefore, the linearity is applicable to a linear networks with no independent sources or no stored energy. So this point please note down. Linearity is applicable, very important point, to a linear network or systems. See, the system is a linear system, no problem, but it should not have any stored energy or independent sources. Network or system with no independent voltage source. See, there are two types of sources, okay, dependent source and independent source. Probably you will be studying this in your circuit theory course, networks and circuits. With no independent sources or no stored energy. So who will store the energy? Inductors and capacitors. This is the condition. Even though the system is linear, but if the system contains an independent source or a stored energy component, then that linearity will go away. Okay, so let me take one example. So let me take one simple resistor. So this is a linear network, right? Why is it called a linear network? Let's say the input is Vi. You apply input Vi to the resistor. I will take the current to be the output. What is the current? I. So this I is going to be V over, or let's say the value of the resistance is R. So therefore I equals V by R. Okay, so if I have two voltage sources, first let me put V1, then the corresponding current let me call I1. Therefore what is the input? V1 gives rise to I1. What is I1? I1 is V1 by R1. Now again apply to the same resistor V2. Now let me call the current I2 now. This I2 is V2 by R. Now what will I do is, let me add these two inputs V1 plus V2. Now this gives rise to a current I. What is this current? V1 plus V2 by R. That means V1 by R plus V2 by R. Now V1 plus V2 gives rise to I1 plus I2. What is I1 plus I2? V1 by R plus V2 by R. Therefore it is a linear. Again this the output is we got here, so both are same, therefore it is a linear device. Now let us consider a situation where the network is not linear. Now as I said, you put some independent voltage sources, then the non-linearity property will go away. Let me put a voltage source like this, let's say 2 volt, and this one is 1 ohm resistor. Now let us see whether this network is linear or non-linear. Let me say the input is Vi and the output is I0. Now you apply two voltage sources. First you apply V1 and let me call the corresponding current I1. What is I1? V1 minus 2 volts divided by 1. So V1 minus 2 ampere. This is the I1 output. So I1 is equal to V1 minus 2. Now let me apply V2. V2 which will give rise to I2. This I2 is going to be V2 minus 2 by 1, because the current always find out by potential difference. Here the potential is Vi and here the potential is 2. So the potential difference is Vi minus 2 divided by the resistance R. So that's the formula I am using now. Okay, so 2. Now instead of giving V1 alone and V2 alone, let me add it, V1 plus V2. So you take the circuit, now put it same 2 volt source, 1 ohm resistor, this is 2 volt. Now let me call this current is I. What is the I? Now I is equal to the potential difference, potential at this point. What is the potential? You are adding these two voltages. Two voltages are in series like this. This is plus and minus, this is plus and minus. Let's say this is V1 and this is V2. You are adding these two voltages. Therefore the current I is this potential minus this potential at this point divided by 1 ohm. Therefore V1 plus V2 minus 2 divided by 1. So therefore total current is equal to V1 plus V2 minus 2. Now as per the superposition principle, if I add V1 plus V2, the output also the addition of these two outputs. Okay, so V1 minus 2 plus V2 minus 2, which is V1 plus V2 minus 4. But this is what you should supposed to get it. But in practice what you are getting, this you are getting. Therefore this is not equal to that one. So the system is non-linear system. This I is not equal to I1 plus I2. Why? Because we have a source here. Because of that source, the non-linearity goes away. So when you apply this non-linearity principle or superposition principle, you must make sure that you are applying it to a network which does not have sources or stored energy for that matter. Let me take one more example. Okay, so suppose I have a capacitor C. The voltage across the capacitor is Vc. okay, which has got an initial stored charge of Vc volts. Initially the capacitor is charged to Vc volt. Now I have a current source, and that current source is connected here. Let me denote this current source by I. So I can think of this as a system in which I is the input, right, input quantity, and Vc as the output quantity. Like you put a black box, the input is I and the output is Vc. Now let me assume that Vc of 0 before, let us say you put a switch like this, you close the switch at time t is equal to 0. Before time t is equal to 0, or let us say now time is 5 o'clock 11 p.m. in the evening. Now I am switching closing the switch at 5:11 p.m. and before that, before 5:11 p.m., before I connect this current source to this capacitor, the capacitor is charged to some voltage. That voltage, let me say rho volts. I don't know, but some rho voltage. Therefore, the initial capacitor voltage across the capacitor is rho volts. Then you have the relation, like you can apply the Kirchhoff's voltage law or current law, and you can find out what is you can find out the relation between input and output. Let's apply this. Let's do it. Like the voltage across the capacitor, now it is a function of time. This is 1 over c integral of current I of t times dt, and integrate from, because you are closing the switch at 5 o'clock 11 p.m. so that is your lower limit, and you wait up to time t, maybe up to 6 o'clock or 7 o'clock or whatever it is you like it. Plus, not only this one, this is due to your source, and also your capacitor has some source voltage, right, initial voltage. That initial voltage is Vc of, let's say 5 o'clock 11 minutes minus before that. Okay, so this is going to be okay. Oh my god, it is not cooperating. Okay, so Vc of 0 it has gone. Vc of 0 equal to rho volts. Then Vc of t is equal to 1 over c. I think some problem with my iPad. Okay, 0 to t. As I said, you are closing the switch at 5 o'clock 11 p.m. Therefore, this is Vc of 5 o'clock 11 before that 11 p.m. before that, so that I put a minus symbol here. So this you remove here, 5 o'clock 11 minutes 11 minutes onwards. Okay, so then you do the integration. Current flowing through the capacitor is I times dt plus this is the due to the source I, and plus due to the what you call initially stored charge. Okay, so that one is Vc of 5 o'clock 11 minutes minus, because I closed my switch at 5 o'clock 5:11 p.m. Now this is 1 over c integral of 5:11 to t I dt plus that initially stored charge is rho volts. That means the voltage across the capacitor now is equal to the initial charge rho volts plus the incremental voltage due to the additional charge that has been conducted to the capacitor in the interval from 5:11 to t. Let me call this is equation number 1. So this is the equation between the input quantity I and the output Vc of t. This is the output and this one is input. Now look at here, we have integral equation, integral differential equation. Now let us take two situations where I have two inputs, let's say I1 and I2. Due to I1 I will get Vc1. Vc1 is equal to 1 by c integral of I1 times dt plus the initial charge rho. If I apply I2, then Vc2, which is 1 over c integral of I2 times dt plus rho. Now instead of applying I1 and I2, let me put two current sources in parallel at a time. I am adding these two guys together, I1 and I2. Now I am giving this to the same capacitor and the same initial charge rho. Now what is output in this case? In this case, voltage across the capacitor, let me call Vc. This is equal to, I am not putting T and all here anyway, that is not needed. You can, if you want, you can put. Vc of t is equal to again 1 over c integral of I1 plus I2 times dt plus rho. So in the input side, I1 of t gives rise to Vc1 of t, right? I2 of t gives rise to Vc2 of t. Now if I add I1 plus I2, it should be equal to Vc1 plus Vc2 of t. What is Vc1 of t? If you look at there, then it is 1 over c integral of I1 dt plus 1 over c integral of I2 dt. I'm sorry, I forgot this constant. Plus rho plus 1 over c integral of I2 dt again plus rho. Okay, so 1 over c integral of I1 dt plus 1 over c integral of I2 dt plus 2 times rho. Okay, this is, but in reality what you got is this one. If we expand this, 1 over c integral of I1 dt plus 1 over c times 1 over c times integral of I2 times dt plus rho. Now you compare this equation, this is the actual output, but this you are supposed to get due to your superposition principle. Now compare this and that, they are not equal. Okay, I1 and I2 respectively will give rise to Vc1 and Vc2. Okay, like if suppose if you add this I1 and I2 and make it as a single source, both of them are acting parallel. That is I1 and I2 together charging the capacitor, like as I drawn here like this. Then your voltage across the capacitor will be given by like this one. Now you can see Vc1, this is my where is it? Yeah, this is my Vc1 and this is my Vc2, and if you add this Vc1 and Vc2, which is not equal to this one. Okay, therefore what spoils is this initial charge, this guy spoils the non-linearity. Therefore whenever you have some initial charge in the capacitor or some initial current in the inductor, then this non-linearity will go. Okay, therefore the principle of superposition is valid only for systems which are purely linear, in the sense that they should not have any independent sources. First point. Okay, this is the first point. Then they should not have initial charges in the capacitor or initial current in the inductor. Okay, so which are always considered to be equivalent to sources. So this is a very, very important principle. Even though your inductors, capacitors are linear element, because of the initially stored charge and current spoils the linearity. So this is a very, very important principle and to keep in mind when you talk about linearity of systems. A system which is not linear is of course called non-linear. So simply you can write that non-linearity. Therefore capital A times x1 of t plus capital B times x2 of t is not equal to A times y1 of t plus B times y2 of t. So this is the condition for non-linearity. So the difference between the linear system and the non-linear system is a linear system is governed by linear differential equations. Okay, let me write down the important points. Okay, so here linear differential equations DE, and here non-linear differential equations. And a non-linear system is governed by non-linear differential equations. So what is the meaning of a linear differential equation? I think probably you may know the definition of linear equations from your mathematics, school mathematics, and your M1, M2, M3 or whatever it is. So linear differential equation is the one in which coefficients of various derivative terms are not functions of the independent variable. Okay, so maybe I'll take some examples later on. So the important point is coefficients are not functions of the dependent variable. That is very important point. It can be function of independent variable. Okay, so if I have a term like d square over dt square, its coefficient should be either a constant a like this, or it could be a function of time t times d square over dt square, but it cannot be like d by d square by dt square, like again d by dt like this. No. Okay, so it cannot be a function of another derivatives of y or y itself like dy like this. So that is not allowed. So linear differential equations are the one which governs the operation of the linear system, and if the equation fails to be linear, then it becomes nonlinear, and that is superposition principle will no longer be valid. So I think let me stop at this point. In the next class I will talk about other classification of systems in continuous time.